Hello everyone, welcome back, and this is our second video in our counting series. We're going to talk a little bit about combinations without repetition in this video. So let's go back to something that we referenced in the first video, which is one of the problems that we solved. So remember those 5 students who received A's in that course, and the way that we solved that problem was we started with 25 factorial. So we said there's 25 objects altogether in this group. That was our n. And then we divided by 25 minus 5 factorial, right? So that was 20 factorial, and 20 factorial tells us to cut off at 20, right? So this is fine, but notice the way that we solved the problem was we actually were giving the order. Right, so one thing that I conveniently left out of that analysis was that this problem shouldn't actually have order, because if you think about those 5 students, now remember, in order to evaluate whether something has order, we look at the box, right? So if we look at the box, those 5 boxes, do you care if you're in this box versus this box? Now, in that problem, all of them receive A's. So the characteristic difference between number 1 and number 5 is exactly the same. Right? So if you're one of those 5 students, perhaps you won't even know if you're number 1, number 2, number 3, or number 4, number 5. So that said, this is not a permutation. It does not have order because the order within the boxes do not matter. Okay, so again, if you're placed number 1 versus if you're placed number 4, you get the same outcome. You get the same characteristic. So in this case, this would not be a permutation. It would be a combination. So the question is, how do we alter this problem in order to make it a combination? So let's think about these 5 people. So let's pretend there are 5 people in this class, whatever this class is, and there were these 5 people. Okay, it's conveniently all of them start with a J. But let's pretend that there's another distribution in which these 5 people are rearranged, but it's the same 5 people. Now, I want to make a note that to these 5 people, these 2 distributions should really be the same, right? So they should not be counted as different. But currently, the answer that I have, 25 factorial over 20 factorial, is counting them as different, right? So they're counting them as different, but realistically, they shouldn't be counted as different. I hope that sounds familiar, because that's exactly what we did in the last example with the ball, like B-A-L-L, that example. So you can probably guess where we're going with this. How many different ways can we reorder these people so that it gives the same distribution? And the answer is 5 factorial, right? So there are 5 factorial ways that we can rearrange these 5 people that would give, theoretically, the same 5 distribution. So whenever there's too much order, remember again, with the LLL, right, the BALLL, we divide off the factorial, right? So this is going to be our final answer, 25 factorial over 20 and 5 factorial. Okay, and again, why we're dividing by this 5 factorial is because we have an overcount for every distribution. We have an overcount of 5 factorial. Okay, so essentially, the 5 factorial comes from the R, the size of the boxes. Okay, so if we're trying to figure out whether something has order or not, it always comes back to the boxes. Okay, so ultimately the way that we're going to look at it is something like this: n factorial over n minus r over r factorial. And we're going to use this notation to indicate this, and we're going to call this n choose r. Okay, so usually whenever you see the word choose in a problem, that kind of hints at you that this is a combination. Okay, so let's go back to that problem that we looked at earlier and see if we can ask it in a permutation form. So as is, right, we said top 5 students get A's. This is a combination because there's no differentiating feature between number 1 and number 5. They all get A's. But what if I said, okay, number 1, the first person in the group gets an A, but they also get $200, right? Second person in the group gets $100. Third student gets 50, and then 25, and then maybe the 5th person gets an A, but they get no money, right? So in this case, now this is a permutation, right? So if we define the problem in this way, now it's a permutation because there is a differentiation between number 1, number 2, number 3, and so on. Okay, now again, another example of a permutation. If we go back to the example or the exercise that we just did at the end of the last video, here we said this is a permutation. Why? Because our 3 places, our 3 boxes, are differentiatable. So what happens if you're in box number 1? Well, I get gold, right? If you're in box number 2, then I get silver, and then third one, I get bronze. So there is a difference between number 1 box and the number 3 box. Okay. Now, on the other hand, what if I said, how many ways are there to choose 3 countries out of these 8 countries, right? I just want to choose a group of 3. Well, choosing a group of 3 is just 8 choose 3 in this case, right? So we have to divide off 3 factorial if that's the case. Okay, so if there's no differentiating feature between these 3, then we have to divide off the 3 factorial. Okay, great. Moving on, let's do another example of this. This is called a combination without repetition. And without repetition, why is it called without repetition? Because still, we cannot be number 1 and number 2 at the same time. Or better yet, Jacob cannot be chosen 2 times in this distribution. Okay, so it's still without repetition. Okay, so in order to play the lottery, you must choose 6 numbers from 1 through 49. How many different tickets can you play? So the way that you play a lottery is that we do something like this. So we have a lottery ticket, and lottery tickets usually are numbered 1 through 49. So you have all of these numbers, right? 1 through 49. And our goal is to take we go into a ticket office, and we just pick, right? So we pick 6 of them, right? So 1, 2, 3, 4, 5, 6, right? So let's say we pick all of those numbers, right? So we choose that, and then that is 1 ticket that we can play, right? So the idea is that from the 46 numbers, we want to choose 6 numbers to play in that lottery. And if we get the ticket, if we get the numbers right, then we win some amount of money, right? So that's the idea behind the lottery. So how many different tickets can you play? So from now on, whenever we answer a counting problem, we're going to ask ourselves 4 questions. Okay, so number 1, what is our n? Okay, so number 1, what is our n? Number 2, what is our r? Number 3, does it have order? Number 4, does it have repetition? Okay, so if we're able to answer these 4 questions, this is going to lead us to one of the equations that we've discussed so far, right? So in this case, we can say that our n is 49. We have 49 objects, and we're placed into 6 boxes. Okay, now does it have order? Well, order means that choosing one of these first is different than choosing another one first, right? So in fact, this one does not have order. Right, so in this case, it does not have order because it doesn't matter which one we pick first. As long as we pick these 6, it doesn't matter which order we pick these numbers. Okay, so it has no order. And does it have repetition? No, because if you pick a 2, you can't pick a 2 again. Right, so no repetition for this question. So quite simply, the answer is 49 choose 6. And there is the solution, 49 factorial over 43 and 6 factorial. Okay, so this is basically the straight application of a combination without repetition. Okay, so we've talked about 3 formulas so far to answer counting questions. We also talked about the sum rule and the product rule, and so all of these things can be used in order to answer questions that we have for counting. So let's see if we can combine some of these techniques together and see if we can come up with or answer some kind of more difficult questions. So first question. In an exam, you must answer 7 out of 10 questions. So let's say this is like an English essay exam or something like that. All I have to do is answer 7 out of 10 questions. Right? So how many different ways can you complete the exam? So basically, how many ways can you complete the 7 out of 10 questions with no restrictions? Okay, so again, we ask ourselves those questions. What is n? What is r? Does it have order? Does it repeat? So we'll find that n is 10 in this case, and r is equal to 7, right? And it has no order because all we need to do is just finish the 10 questions or 7 questions, right? There's no order. I don't have to do question 1 first, question 5 first. It doesn't matter, right? And another way to think about combination is that from 10 objects, I'm just grabbing 7, right? So I'm grabbing all 7 at the same time, right? That's another way to think about a combination. Okay, so in this case, it's just 10 choose 7. Okay, that's all the ways that we can pick 7 out of 10. All right, let's put another variation on that problem. Assuming part A is question 1 through 5 and question part B is 6 through 10. you must answer exactly 3 from part A. So I guess that means that you have to answer 4 from part B, right? So in this case, we're going to answer 3 from part A, and we're going to answer 4 from part B. So there's the product rule again, right? So the product rule, in order to complete the whole exam, I have part A and part B, right? So I have a first stage and a second stage, right? So there's 5 choose 3 ways to complete the first stage, right? Because 5 questions altogether, I choose 3. Again, in no order, right? And then from the next 5, I choose 4. And so to do exactly 3 questions from part A, 5 choose 3 and 5 choose 4. Okay, what about the second question? The second question here says you must answer at least 3 questions from part A. Okay, so you must answer at least 3 questions from part A. So in this scenario, it might be a good idea to use a sum rule. And the sum rule that I'm applying here is called by cases. Okay, so a lot of times when you answer a counting question, we can list out all of the different cases that applies, right? So all of the different cases that applies. So in this case, we must answer at least 3 questions from part A. We can answer 3, we can answer 4, or we can answer 5. Now the or there indicates that we have to add everything together, right? So do 3 from part A, do 4 from part A, or do 5 from part A. And if we solve each of those problems together or separately and combine them, right? So we already know how to solve like one of these problems, right? So if we have each of the cases solved and we add them together, we will get something like this. Now notice that this is a by cases method because we're just taking all the cases and then we're adding everything together. Now in this case, there is a last way to think about this problem, which is I can actually take all of the possibilities, right? So I can take 10 choose 7. So this is all of the ways that I can answer 7 out of 10 questions, but I can subtract the at least 2 questions from part A. Sorry, not at least 2, but exactly 2 questions from part A. So I can subtract 5 choose 2 and 5 choose 5, right? So 2 questions from part A and all 5 questions from part B. So this is illegal in this case, right? So that does not answer at least 3 questions from part A. So I'm subtracting it from the total. And that's the only case that is excluded from the choosing 7 out of 10, right? So this is another way that we can answer, but I think this in general is better because we can have all of the cases and we can just sum them up, and this is kind of like an or kind of thing. Okay, so let's do one more here, another kind of combination of things that we've talked about. So I want to look at the anagrams of the word Tallahassee. So basically, not anagrams, but all of the rearrangements of the word Tallahassee, such that no 2 A's are adjacent. Okay, so here we can deploy, again, a step 1 and a step 2. Okay, so decomposing. So step 1, I'm going to rearrange all the letters that do not have A's. Okay, so I'm going to consider all of the letters that are not A's. And how many rearrangements do we have here? And the answer is 2, 4, 6, 8 factorial. And then divided by, you have 2 L's, 2 S's, and 2 E's. So I'm going to divide off 2, 2, 2, and 2. So this gives me all of the rearrangements of these letters. Okay, now step 2 is I'm going to put the 3 A's back in. Okay, I'm going to put the 3 A's back into this rearrangement. So the question is, where can I put these 3 A's? So I can put them in between any of the letters as long as I only put 1 A in there, right? That will guarantee that there are no adjacent A's, right? So from here, 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 so basically all of these spaces that are in between the letters, I can pick 3 locations to put the A. So there's 9 altogether. Those are 9 arrows altogether. Right? So from 9, I'm going to choose 3. Now, let's think why this is choose. Because if let's say I pick this one, and this one, right? So those are the 3 locations that I decide to put the A in. Does it matter the order in which I pick these locations? No, it doesn't. So the order doesn't matter, and so this is a combination. Okay, now I have to do step 1, and then I have to do step 2. Right? So what we're going to do with these 2 is we're going to multiply them together. Okay, so we're going to do step 1 and step 2. Okay, so again, just applying some of the things that we've talked about so far, and hopefully that makes sense so far. Okay, so getting back to this by cases for 1 second. Okay, so this by cases allows us to be able to solve a problem by summing a bunch of terms together. So notice that like when we solve this by cases method, we were summing these terms, and these terms actually has a pattern associated with it. So we're going to use this thing called a summation notation. And summation notation basically has a variable that has a starting point and an ending point, and it has a term that goes along with it. So all we have to do to kind of take a look at what the terms are is we can take all the numbers from the starting to the end, and we just plug it into the variables. Okay, so I equals 2, and I plug it into there, I will get 2. You should verify this. I equals 3, I will get 6. I equals 4, I will get 12, and so on. And this notation, this sigma notation, just simply means take all of these terms and add them together. Okay, now how this is useful in a by cases method is that we can use that for our summing, right? So in our last example, we said let's do 3 questions, 4 questions, or 5 questions from part A. Okay, so what we can do is we can actually write up a summation that I represents the number of questions done from part A, right? So these are number of questions done from part A. They range from 3 up to 5. Okay? And if I do I questions from part A, it would be 5 choose I. Okay? But the term also contains the B. So for B, I have 5 and then choose 7 minus I. So for example, if I'm choosing 3 questions from part A to do, I will do 4 questions from part B. Okay? 4 questions from part A, I'll do 3 questions from part B. 5 questions from part A, I will do 2 questions from part B. So this is just summation notation, and it gives us a more compact representation for what we're looking at there. And really, the reason for using this would be if we had, let's say 100 cases, right? You probably don't want to write out all 100 cases, and so it's a more compact representation and just reads a little bit better. Okay, so let's do one more quick application of combination, this combination form, and then we can do another we can do another exercise. Okay, let me skip over this for 1 second, and let's talk about very quickly binomial theorem. So binomial theorem is the application that I'm talking about here, and in the binomial theorem, let's say x and y are variables and n is a positive integer. Then it's basically telling us how we can expand x plus y to the n. Okay, x plus y to the n. So when we, for example, want to expand x plus y to the 4, we're going to write out a bunch of variables. So you have a term, which is our variable, and then you also have a coefficient. Okay, coefficient meaning the number that goes in front of the variable. So the variables, we write them out so that we write all the combinations where the x and the y sum to the n. So in our case, our n is equal to 4. Right? So here n is equal to 4, and you can imagine this is x to the 0, right? So our first variable is x to the 0, y to the 4, see, sums to 4. We have x to the 1, y to the 3, sums to 4. X squared, y squared, again, sums to 4. You get the idea, right? And the coefficient that goes in the front is going to be n, choose the exponent for the x. Okay, so we have x to the 0 here, so the exponent for the x would be 0. So we have 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. Okay, so this is actually a really fast way to expand x plus y to the anything, right? So just write out all the combinations so that the sum is n, and then for every one of those variables, what is the coefficient? Okay, so if we consider, for example, if I expand x plus y to the 7, what is the coefficient of x to the 4, y to the 3, right? So we might say, okay, well, according to what we saw before, it's n, which is 7, choose the exponent for x, which is 4 in this case. Okay, now let's just take a little bit deeper dive on this, because if we plug this into our original equation for choose, right, for the combination, we'll get something like this, right? We'll get 3 factorial, 4 factorial. Now, if you consider what this thing is, this is 4 x's, right? So we have 4 x's, and then we have 3 y's. So essentially what we're doing is we're writing the coefficient to say how many ways are there to rearrange the 4x's and the 3y's, right? So if you remember our banana example from the last video, right? So how many ways are there to rearrange this? Altogether, we have 7, right? That's our n, right? So altogether we have 7 factorial. And then there are 3 y's and there are 4 x's, right? So we just write that out. And this, anytime we expand a form, the coefficient always tells us how many ways there are to rearrange the variables. That's what it tells us, right? So even if you're doing FOIL, know that that's what's happening. Okay, so if that's the case, then we can expand our idea of binomial theorem to something a little bit bigger, right? Because what if I have 3 variables? What if it's x plus y plus z? Well, I can apply the same idea, right? What is the coefficient of x to the 4, y to the 3, z to the 2 in this expansion? Now I want you to see that 4 plus 3 plus 2 is equal to 9, right? So that's why we know that there's a variable here like that. And the coefficient is just going to be how many ways can we rearrange 4 x's, 3 y's, and 2 z's? And the answer is this, right? So again, going back to our banana formula, we can just say this is how many ways to rearrange it. So now, great, we can expand as many variables as we want, right? So t variables, and then n could be anything. And when we have a strategy to be able to expand all of these things. Okay, one last application here before we move on. The multinomial theorem, that's what it was called. We can take this a little bit further, and we can even put in the different variables other than x and y. Okay, so what if it's 2x minus 3y, right? So what is the coefficient of x to the 4, y to the 3 when we expand this? Okay, well, that's a little bit harder, but we can do a little bit of substitution as well. Okay, so if we do substitution, we'll find that let's a be 2x and let b be negative 3y. And now we're basically expanding a plus b to the 7. And now we're going to look for a to the 4, b to the 3, the coefficient. Right? So you can see that a goes with x and b goes with y. Right? So that's why we're looking for a to the 4 and b to the 3. Right? And we'll find that in this case, the coefficient is 7 factorial over 4 and 3 factorial. But we're not quite done because we made a substitution at the beginning. We're going to make a substitution back, right? So we're going to substitute a back and now do a little bit of math. And we're going to take the 2 and the negative 3 out of the front, and then now we have our coefficient. So this green part is our coefficient, and this is our variable. Okay, so now using all of these methods, we can now expand basically anything, right? So any formula to the n, right? We would be able to expand something like this. Okay, and that's the multinomial theorem combined with the binomial theorem, and we can have other variables in there as well. Okay, so let's very quickly wrap up this section by going back to the exercise that we looked at a little bit earlier. So let's say that we have 4 extra movie tickets, and you have 14 friends who wants to see this movie. How many ways are there to choose the group who's going to go see the movie with you? So this is just choosing the group. Now choose should kind of give you a hint if there are 2 O's there. So how many ways can you choose a group? Well, the answer is we have n is equal to 14 and we have r is equal to 4. So we always ask ourselves that first. Is there order? In this case, there is no order. So it's just 14 choose 4, which is 14 factorial over 4 and 10 factorial. Okay, so this is without the order. This is, I should also add, without repetition, because you cannot take the same person twice. Right? You can't take the same person twice. You're not choosing the same person twice. But what if these tickets were numbered? So if, for example, one of the tickets was in the front of the theater and another ticket was in the back of the theater and so on, right? So now order matters, right? So if I choose one friend, it's different than if I choose another friend at a particular location, right? So if I get chosen first, maybe I sit at the front. If I get chosen third, maybe I sit at the back, right? So that makes a difference. So the only difference here would be that this is 14 factorial, and then 14 minus 4 factorial, so 10 factorial. Okay, in your 14 friends, you have 6 boys and 8 girls. You would like a group of 4 to have exactly 1 boy. So here we can break it into our product rule, our step 1 and step 2. So step 1 would be choosing the boys, so 6 choose 1, and then that would leave 3 girls that I need to choose. So times, because this is and, 8 choose 3 girls. Okay, what about at least 1 boy? How many ways are there to choose the group? So in this case, maybe we can work on our summation notation. So let's say our I represents the number of boys that we take. So I'm going to take any amount from 1 all the way up to 4, right? So I can take as little as 1, but as many as 4, because we only have 4 tickets. So we can do something like 6 choose I. 6 choose I means that I choose I boys, but when I choose I boys, I'm going to have to choose 4 minus I girls. Okay. So in this section, we were basically talking about combinations, but we focused more on combinations without repetition, right? So we can't choose more than one, an object more than once. So in our next video, what I want to do is talk about the last type of counting problem, which is a combination with repetition. Okay, so I'll see you guys then.